Hey, what's up guys? Welcome back to another video in the Deep Learning with Tensorflow series. In this video, I'm going to teach you guys how to build models using the Functional API. Up to this point, we have been building sequential models using TensorFlow Keras. Sequential models are the most simple. They have one input and one output, and they work sequentially from top to bottom. This is great for all the types of things that we've been doing so far, like binary classification, single label classification, regression, stuff like that. But for anything more complex, where you need to have, for example, maybe multiple inputs, multiple outputs, using a layer multiple times, all kinds of stuff like that. Anything like that with an advanced configuration is not really possible using a sequential model. So that's where the Keras Functional API comes in. This method allows you to really easily build models just like before, but with more complexity and also customizability. Let's start by just showing you how to make a simple neural network using the Functional API. And then what we'll do is we'll take our MNIST classifier and translate it from the sequential model to the functional API model, okay? So in terms of the model that we want to build, you're always going to have an input, you're always going to have an output. The only thing that's different is that with the functional API, you can have multiple inputs and multiple outputs. Let's just focus on making a very simple model with one input. So we're going to do inputs is equal to keras.input. So same import as we did before when we were creating our sequential model, we're simply going to import keras.input. Except that this time we're going to store it in a variable here. And also just like before, we're going to specify the shape of the samples being fed into this model, into the input. So what this means is that every single sample we feed into the model, into this specific input here, it's going to have a shape of 3. So 3 elements. So let's just go ahead and add our first hidden layer. So we'll do x is equal to keras.layers.dense. We're going to do 4 neurons. We're going to do an activation of ReLU. And then now after that, we're going to basically take the output of our input layer and feed it into this new dense layer by simply specifying inputs. So all this is doing here is creating a new instantiation of a dense layer, and then this part after will configure it so that it takes the output of the input layer and feeds it into that layer, that new layer. And we can add multiple, so we can copy this, add a new line. So now we're adding a second hidden layer. We're going to specify to have 2 neurons have an activation of ReLU, but this time instead of taking the output of the input layer, we're going to take the output of the first hidden layer. So this would just be x. And you can repeat this process as many times as you want to. You can add as many layers as you want to. But finally, you're going to have an output. So we're going to do keras.layers.dense, and we're going to have one output neuron, no activation, and then this will tell it to take the output of the last hidden layer and feed it into that output dense layer. Now that we have our inputs, we have our outputs, and we have our hidden layers in between, we can now actually create the model itself by doing model is equal to keras.model inputs is equal to inputs. If you have multiple inputs for your model, you can specify that as a list. You can have outputs. We only have one outputs, so outputs. And you can also give your model a name. So we can say simple model. And then once you're done, you can visualize it by doing model summary. Here we go. So here's our model. This is hopefully familiar to you. So we have our model, which is named simple model. We have our input layer that has an output shape of 3. We have our first dense layer. This has 4 neurons. Second dense layer has 2 neurons. And then our output layer is just 1. If we want to, we can add names to these. So we could do name is equal to hidden 1. We could do name is equal to hidden 2. And then for our output, name is equal to output. So let's run this again. There we go. So now that I think is easier to understand here. And now once we have defined our model using the functional API, everything else from that point is pretty much the exact same. So we can do model.compile, and we could pass in, our optimizer, mean squared error, MAE, and then fitting is the same as well. We don't really have any data. We're just focusing on making the model, but it's the same thing. So hopefully this all made sense. This is how you can create your very first functional API model. Behind the scenes is really the same thing. It's just a Keras model. It's just that the way that we're creating it is different. I think this syntax is a little confusing at first, but the more you work with it, of course, the easier it is to understand. Basically, we just define our inputs, however many we have. In this case, we only have one input. And then after that, you define how the input is fed through the network. So we have our 2 dense layers in the middle here. We're taking our inputs, feeding into the first layer, and then we're taking the output of that first layer and feeding into the next hidden layer. And then we're taking the output of that second hidden layer and feeding it into our output layer. So as you can see with the functional API, it is more customizable because you're manually having to specify which outputs go to which inputs and so on, okay? So you have much more customizability, and of course it's just more complex. You just have to understand what's going into what and whatnot, but yeah, you can customize it a lot more. And then once you have all that defined, you create your actual model, you define your inputs, you define your outputs, give it a name if you want to, and yeah. Something cool that you can do with this is actually visualize it. So you can do keras.utils.plotModel. This is a function And what you can do is specify the model that you're trying to plot. Mine is just model, as you can see right here. So we're trying to plot that model. I opened it in a new tab. Here's what we get. We get this little diagram here that shows how the layers are configured for our network. So we have our input layer, dense, dense, dense. And then if you want to, you can specify more information like to a specific file, show shapes, show the data types, show the layer names. Let's try that one. So show layer names. We'll say true or true like that. And then we can also do show shapes. Set that one to true as well. There we go. So now we get a much more detailed diagram here. So we have our input layer. We can see it as an output shape of none and then 3. And the reason it says none, by the way, is because that's specifying the batch size. But for this particular network that we're doing and the other networks that we've made so far, our batch size can be anything. It's variable batch size, so it's not like a fixed specific amount. So that's why it says that. So then that gets fed into our first hidden layer. That has the name of hidden 1, which is nice. You can see that has the input shape of 3. That's how they're compatible. So this outputs 3, this takes in 3, and then this outputs 4. This one takes in 4, outputs 2, so it's descending in terms of the dimensionality. And then the output layer takes in that 2 and then outputs 1. This little tool here is very helpful, especially as your models get more complex, as we're about to see. Speaking of which, let's take a look at this code here, which creates a model using the functional API, but it has multiple inputs. So I think it's actually helpful to visualize it first. Let me open this up. So as you can see, we have two inputs. We have input 1. This has an output shape of 32, so it's taking in 32 elements per sample. And then this one has an input with only a shape of 16, so it's smaller. One reason, for example, that you may want to have a network with multiple inputs is when you have information that is in multiple modalities or multiple forms. So, for example, if you're processing image data, you may want to take in the images in one input and then also take in the metadata of the images in another input and then process them independently. And then at a certain point in time, you may want to combine that information inside of your network and produce an output for it. So differing sources of information for a network is why you may want to have multiple inputs, okay? So for this first input layer that we have here, we can see that it takes in 32 per sample, and that gets fed into a dense layer, which has a output shape of 64, so it has 64 neurons. And then that gets fed into another dense layer, which has 32. That is completely separate from our second input layer, so that's getting processed independently. And so for the second input layer, this just gets fed into a dense layer that has 32 neurons. And then after that, these two sub parts of your network are concatenated using this concatenate layer. So this is a new layer that takes in multiple inputs and literally just combines them together. So for example here, this dense layer that we have here has an output shape of none 32, so it has 32 elements per sample as a vector. And then this dense layer has 32 as well. Concatenating just means to add. So when they're both fed into this concatenate layer here, you're just going to combine the results into one output. So that's why it takes in 32 and 32 and outputs as 64. And then that combined output will be fed into a dense layer, which has 64 neurons, then 32 neurons as another layer. And then finally, there's an output layer, which has an output shape of 1. Let's take a look at how we can actually achieve that. So just like before, we're going to define our input, except that we're going to have multiple. So we're going to create multiple variables here. So input 1, creating a new Keras input, specify the shape of the input, give it a name if you want to. And then input 2, shape is 16, not 32. Input 2 is the name. These are two separate variables. And then for input 1, we have those two intermediate layers at the top here. So top left, we have dense 7 and dense 8. This is what that is. So we're creating a new dense layer here. We're taking the output from the input layer, feeding it into that dense layer, and then we're going to feed that into a second dense layer. And then for input 2, we're taking the output of input 2, feeding it into a single dense layer of 32 neurons. So now at this point, we have x1, which is the results from this first little branch here, and then we have x2, which is the results from this second branch here. And now we want to combine them together, concatenate them to create a single output essentially for each sample. So this is where we create that concatenate layer, so instantiate it, and then now we're passing in a list of both of the outputs. So that will do its thing. It's going to merge it together. And then we're going to feed that merged information into two more hidden layers, so dense 10 and dense 11, and then finally into an output. So we're creating the new dense layer here, feeding in the merged or concatenated information, and then we're taking it and feeding into a second hidden layer. So X will have all that. And then now we're taking the output of X and feeding into our output layer. So our output layer has a single neuron, it has an activation of sigmoid, and then it has the name of output. So once you have defined all of that, you can then create your model. So we're going to do models equal to new Keras model. And then for the inputs, since we have multiple inputs, we're going to provide it as a list. So input 1, input 2. And then for outputs, we only have one output still. So just provide output like that. And then from there, just compile your model. So model.compile, optimizer atom, binary cross entropy, accuracy. here's the summary. So the summary, as you can see, is much more complex than we normally get. So here's our input 1, input 2. We can see that we have these random dense layers. It may be helpful in the future to give them names that more quickly identify them as being part of this input 1 or input 2 sub branch here. You also have this random dense 10 layer, and you may be wondering, what does that connect to? Let's just say that you don't have this little diagram here. To know which one that connects to, you simply look at the connected to column, and you can see that it's connected to the concatenate layer. So hopefully that all makes sense. That's how you can create a model with multiple inputs that feeds into a single output. So hopefully all of that makes sense. The functional API, the way it works, how you can specify the information that's going to these individual layers here. I think visualizing it really makes it a lot more easier to understand. Let's use what we've learned so far to also translate our MNIST classifier to, instead of using the sequential model, use the functional API that we just learned about. So just as a little bit of a reminder here, we're just creating a very basic model. It has a flattened layer, so it's taking the image input and flattening it to be 784, and then it's feeding that into a hidden layer, a dense layer with 128 neurons, and then to a second hidden layer with 64 neurons, and then to an output layer with 10 neurons, because we're trying to do single label multi-class classification. And so there's 10 options to choose from, 0 through 9. So let's start by just commenting this out. First things first, we always want to define our inputs for our model. So inputs is equal to Keras.input. So the shape that we want is 28 by 28, just like we have above, because the grayscale images that we're feeding in from the MNIST dataset is a bunch of images that are 28 by 28. So that's what the model should expect for the input layer. Afterwards, we want to feed that into a flattened layer, same as before. So we're going to make a new keras.layers.flatten. And then we're going to take the output from our input layer and feed it in like that. So inputs, then we'll feed into the first hidden layer. So I'm just going to go ahead and copy this part like that. So boom. So that's going to be our first hidden layer. And then we're going to pass the input from the previous layer into that new layer. And then we'll literally just copy this, hidden 2, and then we're going to have this one be 64 neurons, okay? Now finally, we're going to have our output layer. So outputs is equal to, boom, and then we're going to add our x. So the x from the previous layers will be fed into this output layer, and that's it. So now we can go ahead and actually create the model, instantiate it. So model is equal to keras.model. And first we got to pass in our inputs. So inputs is equal to inputs, outputs is equal to outputs. The name we can call it, same as before, the MNIST underscore classifier. Okay, so I ran the model through the training process, and then I also evaluated it on the test set, and we have similar test loss and accuracy, so that's good. This means that, the model's still working the same behind the scenes, it's just that we created the model a different way. And the reason that the results are different is just because of the randomization of the weights of the model and other factors like that, so you won't get the same exact result every single time. I'll give you guys an even more complex example here. So now we have a model that has multiple inputs and multiple outputs. This source code is from Deep Learning with Python 2nd edition, just like most of my source code for the series. Just making sure to provide credit where credit is due. This is going to be a neural network for a ticket processing system. You can think of a ticket as like a help email, like for a company you submit like a request, like can you help me with something? So it has like a subject and a body, so like kind of like an email pretty much. The model is going to have two outputs, which is the priority score of the ticket, so how important the ticket is, and then the other output is the department that should handle the ticket. So that part will be a classifier, so it should produce one of many categories for the different departments that are available to us. Let's just go through this code step by step. So first, you're going to define your different inputs. So we're going to have a title, which is the subject of the ticket, or the title of the ticket. We're going to have the text body, and then the tags. These text inputs that we have here are going to be encoded like we did before as vectors with numbers that correspond to a vocabulary that we have. So for the title, we're going to create a new input, define the shape, which is based on the vocabulary size, so every vector should be of that size. Also very important, since we have multiple inputs, you should give it a name so we know what is what. And then we have text body, so this is also based on the vocabulary size because it's text information. It's called text body, and we have tags. This one's going to be based on the number of tags that we have or the number of categories, and we have it hard-coded as 100. So those three inputs are going to be fed immediately into a concatenate layer. So it's going to take all the inputs and combine them all together into a single vector per sample. So that is what features represents. It's the combined results of all the inputs. And then that's going to be fed into a single dense layer with 64 neurons and activation of ReLU. After it's fed through that hidden layer, we're now going to output into two different output layers. This is because we want to predict multiple things, like I said. First, we want to predict the priority of the ticket, but then also predict the department that it should be a part of. Like what department should handle this ticket, right? So since we have those two requirements, we want to have two different outputs, right? So first we'll have our priority output, so layers.dense, as a single neuron because we're just doing a number 0 through 1 that represents the priority of the ticket. It's going to be an activation of sigmoid because that will squash it to a range of 0 to 1. We'll give it a name of priority so we know what the output represents. And now we're going to take the output of features, which we fed through that concatenate and dense layer, and feed it into that output. And then independently, we're going to have another output. This is going to be a dense layer. It's going to have the size of it will be dependent on the number of departments that we have. So we only have 4 departments. So we're trying to predict one of 4 different options. It's going to have an activation of softmax because it's a single label classification problem. We'll give it a name of department. So hopefully that all makes sense. I really hope it does. So we have our 3 inputs. We have our intermediate layers, which is our concatenate layer, and our dense layer, which is 64 neurons. You can add as many as you want though. And then now those results are going to be fed into 2 different output layers, priority and department. Okay. So when you instantiate your model, you can do model is equal to keras.model. We have multiple inputs, so we'll do a list of inputs, so title, text body, tags. And we have multiple outputs now, so we're going to do a list of priority and departments. So in terms of actually training this model that we've built using the functional API, I told you before that compiling the model and fitting the model is the same as before, but now that we have multiple outputs, we have to do it a little bit differently. So first of all, we're just going to randomly generate the actual data that we're going to feed into the network. So we'll do this number of samples, we'll generate the data randomly. Then we're going to compile our model, so we're going to use an optimizer of RMS prop. You can use Atom, you can use whatever you want. And now for the loss, usually we specify only one loss, but since we have multiple outputs, different outputs do different losses as we learned, right? So we want to specify a list of outputs corresponding to each of the outputs that we have. So since our first output is a number-based output layer, we're going to do mean squared error. And then our second output is a single label prediction, so we're going to do categorical cross entropy. And then for the metrics, it's pretty much the exact same thing. Usually for metrics, we specify multiple metrics per output. But since we have multiple outputs, we're going to do a list of lists. So the first list will be all the metrics that we want to use for the first output layer. And then the second list will be all the metrics we want to use for the second output layer. And then for actually fitting the model, for training it, we want to specify a list for the inputs. So this data here goes into the first input. This goes into the second input. This goes into the third input. And then for the Y, so that we have the actual values for our outputs, we have priority data and then department data. So for the first and then the second. And then for evaluate and predict, it's the same story. Since we have multiple inputs and multiple outputs, we want to provide lists. So if we use that plot function we learned about before, this is what it looks like. So we have our first input, our second input, and our last input. That is fed into our concatenate layer, so it's all combined together. Then it's going to be fed into our dense layer, and then that dense layer will be fed into 2 different output layers. Something interesting about the functional API, since you're doing everything sort of from scratch, you're building these layers independently and specifying what output goes into what input and whatnot. You can also do stuff like this, so you can do model.layers. So this will give you literally just a list of all the layers of your model. So you can literally just pick and choose a specific layer from a model. So for example, we can target the 4th layer of our network. So that would be the concatenate layer. And then we can get just the input. You can see that for this input here, it's a list of 3 different tensors. And hopefully this makes sense because our concatenate layer, as we know, takes in 3 different input layer outputs, right? So this specifies the shapes of the different inputs that we're feeding into it. So for our title, we have 10,000 in size per vector, 10,000, and then 100 for the last input. And then for our output, we only have one tensor here, which tells us information like the shape of the output, the data type, and whatnot. We can see that this number makes complete sense because we're adding together all the outputs from our input layers. So since you can basically selectively target different layers of a model that you already have, you can build a new model off another model by basically hijacking. I don't know if hijacking is the right word. You can take one of the layers of another model and add more layers onto it, basically, right? So for example, this one here is targeting our 5th layer. So 1, 2, 3, 4, 5. This would be our dense layer after our concatenate. What we're doing is we're taking this and adding another layer onto that. So we're creating this difficulty layer. So this has 3 neurons. It has an activation of softmax and has the name of difficulty. And this will take those features, feed it into that layer, and then output a value that represents the difficulty of the ticket. So we're taking this new layer that we have here, we're creating an entirely new model. We're telling it the inputs are going to be the same inputs as our original model. And then for the outputs, we have our 2 outputs that we have in the original model plus a new output that we just added. So basically we've defined a new model which piggybacks off the architecture of the first model. So this is what it looks like, same as before. We have 3 inputs, 1, 2, 3. They get concatenated together. It's fed into a dense layer. But now instead of 2 output layers, we have our 3rd output layer added to it. So that's all I got for you guys this episode. Now you guys should know how to use the functional API to create even more complex models with more complex layouts. Hopefully you found this interesting. In the future though, just as a general rule, you can use whatever API you want, the sequential model API or the functional API. It really just depends on what you like, what you prefer, but also what use cases you have. If you have relatively simple models like we've been doing so far, you can just make a sequential model. But if it's more complex, obviously, you may want to use the functional API. So in the next episode, I'll be showing you guys one more way you can create TensorFlow Keras models, okay? So that's it for this video, everybody. I really hope you learned something new. If you liked the video, please hit the like button, and if you want to see more, hit that subscribe button. Make sure to also check the description below for important links to code and other resources, but also really important, join our Discord. We have a big community of over 5,000 programmers, and it's a place where you can find new friends or get help on any code that you're stuck on. If you want to support what I do on this channel, please consider hitting the join button below, and this will allow you to support my channel for as low as $1 a month, but there are different tiers to choose from if you want to. For anyone that becomes a member on my channel, you get a special rank on my Discord server, early access to new videos, and you can just see yourself on the screen right now. So if that sounds cool to you, feel free to join. If you don't want to, that's fine. If you can't, that's okay too. I really just appreciate you watching the video anyway. Thank you so much. And that's it. Peace.